Which of the following rings are principal ideal domains? Option A, Zx upon ideal x square plus 1. Option B, Zx. Option C, Cx comma y. Option D, Rxy upon ideal x square plus 1 comma y. So Zx upon ideal x square plus 1 is isomorphic to z iota because roots of x square plus 1, these are x is equals to plus minus iota. So simply we need to put the roots in this ring Zx. So it will be z iota. And z iota is ring of Gaussian integers, which is an Euclidean domain. And we know that every Euclidean domain is a principal ideal domain. So z iota is a PID and z iota is isomorphic to Zx upon ideal x square plus 1. So this is a PID. Option B, Zx. As Z is not a field, so Zx is not a PID. In option C, if Cx comma y is a PID, then I can write this as Cxy upon ideal y, and roots of this y are 0 only. If I put 0 in this ring, then I will get Cx. So if Cxy is a PID, then Cx is a field, which is a contradiction because polynomial ring is not a field. So Cxy is not a PID. Next is R x comma y upon generator x square plus 1 comma y. So firstly find the roots of this y equal to 0, put in this ring R. Then this is isomorphic to Rx upon ideal x square plus 1. Roots of x square plus 1 are plus minus iota. Put this x equal to plus minus iota in this ring R. So this will be R iota. R iota is basically complex numbers only. Now since complex numbers is a field and every field is a PID, so this means that C is a PID. Now C is a PID and C is isomorphic to the given quotient ring. So R x comma y upon ideal x square plus 1 comma y. This is a PID. So option D is also correct. So answer for this question is option A and D. Next question. Again a part C question. Which of the following polynomials are, screen visible है ना? हाँ जी. ठीक. Irreducible in Zx. Option A, x to the power 4 plus 10x plus 5. Option B, x cube minus 2x plus 1. Option C, x to the power 4 plus x square plus 1. Option D, x cube plus x plus 1. Try this question.
A and B.
Yes. So what was your approach for option A?
Option A तो Einstein's criteria.
ठीक है. So this belongs to ZX. So what was the prime number P you have taken?
5.
ठीक है. So 5 divides 5. 5 divides 10. 5 square does not divide 5. 5 does not divide 1. So by Eisenstein criteria, fx is irreducible over integers. Option A is correct. Option B, x cube minus 2x plus 1. How you have done this? Option B.
मैंने तो इसको लाइक जीरो का पॉलिनोमियल फाइंड करके x को 1 पुट करेंगे तो जीरो हो रहा है, तो x माइनस 1 इसका रूट बन रहा है, तो इसलिए ये रिड्यूसिबल हो जाएगा ना.
ठीक है. x cube minus x plus 1. So I can take x common, x square minus 1, minus 1 common, x minus 1. So x minus 1, x square minus 1. So this is finally x minus 1 का, एक second, x into x square minus 1 minus of x minus 1, x minus 1 common. यहाँ x plus 1 बचेगा. X into x plus 1 minus 1. So x minus 1, x square plus x minus 1. So this is clearly reducible over z. So option B is wrong. Option A is correct. Option C, x to the power 4 plus x square plus 1. So how you have done this?
इसको मैंने स्क्वायर बना लिया ना, आइडेंटिटी बना ली. x स्क्वायर प्लस 1 है ना, तो 2x स्क्वायर कर दिया और एक x स्क्वायर माइनस कर दिया.
ठीक है.
I've written it like this: x4 plus 1 plus 2x square minus x square.
ठीक है. Plus x square minus x square plus 1. So x to the power 4 plus 2x square plus 1 minus x square. So this first bracket is x square plus 1 का square minus x square. So a square minus b square identity. So x square plus 1 minus x square plus 1 plus x. So this is also reducible polynomial over z. So option C is also wrong. Option D, x cube plus x plus 1. So how you have done this?
इसको तो मैंने डायरेक्टली किया है क्योंकि यहाँ पे जीरो कुछ बन नहीं रही थी, और दूसरा चीज की डिग्री 3 का जो पॉलिनोमियल है वो इररिड्यूसिबल हो सकता है ना.
बेटर ये होता मॉड पी इरिड्यूसिबिलिटी टेस्ट लगा लेते तो कंफर्म हो जाता.
अच्छा, वो नहीं लगाया.
ओवर z2 देखा. So f0 is 1, f1 is 3, modulo 2 1. Both are non-zero. So f bar x is irreducible over z2. So fx is irreducible over z. So option D is also correct. So answer is option A and D. Next, let R be a subring of rational number containing ideal I. Then which of the following is necessarily true? Option A, R is a principal ideal domain. Option B, R contains infinitely many prime ideals. Option C, R contains a prime ideal which is not a maximal ideal. Option D, for every maximal ideal M and R, the residue field R by M is finite. Factor ring or quotient ring or residue field, these are same. Containing 1 means unity. This is part B question, MCQ.
ये नहीं समझ में आ रहा कैसे अप्रोच करेंगे। रिजल्ट
डिस्कस कर लेते हैं। So it is given that R is a subring of rational numbers which contains 1 means unity. So I can take R as rational numbers only. This is a subring of rational numbers containing unity. Now firstly I am discussing option B. Option B is saying R contains infinitely many prime ideals. Rational numbers is a field, and we have discussed if there is any field then it contains only two ideals. Q has only two ideals, 0 ideal and rational number itself. So this means that Q will have finitely many prime ideals. So option B is wrong because it was saying that Q has infinitely many prime ideals. Now option C, Q contains a prime ideal which is not a maximal ideal. Q does not contain any prime ideal which is not a maximal ideal. Now for option D, for every maximal ideal M in R, the residue field R by M is finite. Now if I pick a maximal ideal from this is maximal ideal of rational. So R by I means Q by 0. This will be isomorphic to rational numbers only, and this rational number is not finite na? When this is not finite, then residue field cannot be finite. So option D is also wrong. Now as options B, C, D are discarded, answer is option A. Also note that a subring of the field of fractions containing unity of a principal ideal domain is a PID as well. A subring of the field of fraction. Here field of fraction was R by I and R was a subring. Containing unity was this, of a PID. Rational numbers is a PID as well. That's why answer is option A. R is a PID. Next, consider the ideal I is equals to x square plus 1 comma y in the polynomial ring Cx comma y. Which of the following statements is true? Option A, I is a maximal ideal. Option B, I is a prime ideal. But not a maximal ideal. Option C, I is a maximal ideal but not a prime ideal. Option D, I is neither a prime ideal nor a maximal ideal.
First option.
नहीं.
No. Yes, ma'am.
फर्स्ट ऑप्शन नहीं है.
क्योंकि c upon x square plus 1, so it will have the units x belong करेगा उसको, तो c by x square plus 1 फील्ड होगा ना, तो x square plus 1 maximal होगा. It is isomorphic to cx. Right.
और अगर सिंपल बाय डेफिनेशन देखें तो
एक मिनट.
प्राइम आइडियल चेक करो पहले सिंपल बेसिक डेफिनेशन से. So if we see that x square plus 1 belongs to I.
ठीक है, मैक्सिमल नहीं होगा, प्राइम हो सकता है.
देख लेते हैं यहीं पे, प्राइम ही चेक कर रही हूँ मैं. एंड I is equals to ideal x square plus 1 comma y. So this means that x square plus 1 can be written as x minus iota into x plus iota. This belongs to I because I can write x square plus 1 as x square plus 1 into 1 plus y into 0 in this form. So you can clearly see that neither x minus iota belongs to I nor x plus iota belongs to I, because definition was that AB belongs to P implies either A belongs to P or B belongs to P, then only it is a prime ideal. So here I is not a prime ideal. So by doing this, option B is wrong because it is saying that I is a prime ideal. Also, we know that every maximal ideal in a commutative ring with unity is a prime ideal. Now its contrapositive will be not a prime ideal implies not a maximal ideal. So as I is not a prime ideal, so I is not a maximal ideal. Simple basic definition. So answer is D part. I is neither a prime ideal nor a maximal ideal. Next, which of the following statements are true? Option A, Zx is a PID. Option B, Zx comma y upon ideal y plus 1 is a unique factorization domain. C part, if R is a PID and P is a non-zero prime ideal, then R by P has finitely many prime ideals. Option D, if R is PID, then any subring of R containing unity is again a PID.
फर्स्ट तो रॉन्ग है, जेड इज नॉट अ पीएलडी। जेड एक्स वाई अपॉन वाई प्लस वन, यहाँ पे वाई इक्वल टू -1, तो -1 तो इसमें है जेड में। तो अगर हम यू एफ डी, तो दैट मीन्स
zxy upon ideal y plus 1.
वाई प्लस वन इक्वल टू 0, वाई इक्वल टू -1, 0 देगी ना।
This can be also written as zx and y, this type. Means I can also write ring rxy as rx and then y. Ideal y plus 1. So this is ry upon ideal y plus 1, where r is equals to zx. So I am defining f mapping from ry to the roots of this ideal. This y function of hy, this is equal to h minus 1, because roots of this ideal is -1. Can you please mute yourself? Now clearly f is a ring homomorphism and it is onto also. So by fundamental theorem of ring homomorphism, ry upon kernel of f is isomorphic to r. Now what will be kernel? Kernel f is equals to hy belongs to ry such that fhy is equals to 0. So this is equal to hy belongs to ry such that h minus 1 is equals to 0. So this will be ideal y plus 1 because this ideal has root 0. So ry upon ideal y plus 1 is isomorphic to r, implies zxy upon ideal y plus 1 is isomorphic to r, and ring r was this zx. So zx upon y plus 1 is a UFD because zx is a UFD, and zx is isomorphic to zxy upon generator y plus 1. यहाँ पे zxy आना था, comma y. ठीक है, so that's why option B is correct. Now option C, if R is a PID and P is a non-zero prime ideal, then R by P has finitely many prime ideals. Option C, if R is a PID and P is a non-zero prime ideal, so this means that P is maximal ideal. Because we know that in case of PID, every non-zero prime ideal is maximal and every maximal ideal is prime in case of PID. So By this, P is a maximal ideal, and as P is a maximal ideal, so the quotient ring R by P is a field, and we know that a field has only two ideals. Zero ideal and itself. So clearly R by P has finitely many ideals. So basically results को interconnect ही करना है, इसलिए रिजल्ट ध्यान में होने जरूरी है. So option C is correct. Last option is, if R is a PID, then any subring of R containing 1 is again a PID. So if I take ring R as Rx, this is a PID. Now I take a subring of this ring R, this be a subring of Rx with unity 1, which is not a PID because Z is not a field. So option D is wrong. So answer for this question is option B and C. ये वाला क्वेश्चन मैं होमवर्क के लिए दे रही हूँ, उसे ट्राई करना. Which of the following polynomials are irreducible in the ring Zx of polynomials in one variable with integer coefficients option A x square minus 5, option B 1 plus x plus 1 plus x plus 1 का square plus x plus 1 का cube plus x plus 1 to the power 4, option C 1 plus x square plus x cube plus x to the power 4, option D 1 plus x square plus x cube. Next question. Determine which of the following polynomials are irreducible over the indicated rings. Option A x to the power 5 minus 3x to the power 4 plus 2x cube minus 5x plus 8 over real numbers. Option B x cube plus 2x square plus x plus 1 over rational. Option C, x cube plus 3x square minus 6x plus 3 over integers. Option D, x to the power 4 plus x square plus 1 over z by 2z. ये दोनों ही क्वेश्चन पार्ट सी के थे, MSQ. मोर देन वन ऑप्शन कैन बी करेक्ट. Which of the following is an irreducible factor? Of x to the power 12 minus 1 over rational numbers. December 2015 question. Part B. Option A, x to the power 8 plus x to the power 4 plus 1. Option B, x to the power 4 plus 1. Option C, x to the power 4 minus x square plus 1. Option D, x to the power 5 minus x to the power 4 plus x cube minus x square plus x minus 1. ये सारे क्वेश्चंस जो होमवर्क में दे रही हूँ ना, ट्राई कर लेना ताकि कोई डाउट आए तो कल हम डिस्कस कर सकें. Which of the following polynomials are? इरेड्यूसिबिलिटी पे हम हमेशा एक क्वेश्चन एक्सपेक्ट कर सकते हैं, तो इस टॉपिक को ध्यान से करना. काफ़ी बार रिंग थ्योरी में कुछ कॉम्प्लिकेटेड क्वेश्चंस आ जाते हैं, तो इरेड्यूसिबल वाला इतना कॉम्प्लिकेटेड नहीं आता. ऑप्शन ए, एक्स टू द पावर 4 प्लस 10x प्लस 5. ऑप्शन बी, एक्स क्यूब माइनस 2x प्लस 1. ऑप्शन सी, x to the power 4 plus x square plus 1. Option D, x cube plus x plus 1. ठीक है, सारे क्वेश्चंस ट्राई कर लेना.
ओके.
फिर इसके बाद कल से हम कॉम्प्लेक्स एनालिसिस स्टार्ट कर देंगे.
राइट.
ठीक है.
थैंक यू.